Welcome to the Metal Casting Concepts virtual seminar. First article approval success. How, who, what, and why. My name is Julia Speaker. This is part one of a two-part webinar series. You will be notified well in advance of the broadcast date and time for part two. This seminar is funded by the Defense Logistics Agency, and it has been developed by the American Metal Casting Consortium's Casting Advanced Systems Technology Integration Team, also known as CASTIT, to assist DLA in achieving a higher success rate in metal casting first article approvals. Among the objective of CASTIT is improvement in procurement lead times and cost for low volume cast metal components for aged weapon systems, also called legacy castings for short. Among several CASTIT contributors appearing in this seminar, we will address why first article approval success is difficult for castings in general and especially difficult for DLA's legacy casting procurements. Specific to legacy casting procurements, we will address what the roles and responsibilities are among the casting producing team, the first article inspection laboratory, the engineering support activity, and the Defense Contracts Management Agency. Finally, we will address how each role's responsibilities can be executed more effectively and faster for the sake of the warfighter's need for aged weapon systems readiness when cast metal replacement parts are needed. So that you as an attendee can interact with our team's presentation, I will enable a chat box now so that you can document questions, comments, and discussion points as the seminar progresses. At the conclusion of the presentation, I will return to combine your chat box inputs for comments by our team. So let's get started. Here is Mike Gwynn, our CASTIT expert on casting design and manufacturing engineering.
Whether low-volume DLA procurements for legacy castings to support an aged weapon system, a launch of a new casting design for a current weapon system, or those same two situations for any commercial manufactured product that contains castings, first attempt, first article approval success is difficult and usually involves at least one disapproval or at least one conditional approval. When just comply with the specifications is the route to no nonconformances, what makes metal casting so much more difficult to comply? Our objective is to explain why, then explain the pathway to a successful first attempt success, and explain who was responsible for what to make that happen. DLA has done an excellent Pareto analysis of the reasons for legacy casting first article nonconformances. For our attendees who are defense primes and commercial OEMs, the high-frequency reasons for legacy castings are the same ones for new weapon system casting designs as well as any commercial first article casting submission. So what we're addressing is a pervasive problem among all casting first article approvals.
Here's the Pareto chart that I referred to. Among 1,040 reasons for casting nonconformances, the 383 that are encircled in tan are specific to dimensions and surface finish. And that's 37% of all casting nonconformance reasons. The nonconformances with a star, these, including those encircled, are specific to either the casting tooling or the casting processes. Among those with the star, those encircled dimension and surface finish nonconformances are 89% of the reasons for nonconformance. So, dimensions and surface finish are by far the biggest problems that castings suffer in first article inspection nonconformances. Let's investigate why. The major and most difficult to solve problem in making casting dimensions comply with tolerance specification is the phenomenon I call pattern maker's contraction, commonly referred to in metal casting jargon as the shrink rule. When materials solidify from liquid, most of them, including all metals, form a crystal structure that's smaller in volume than the atomic arrangement in the liquid. This is different from solidification shrinkage, so that's why I prefer to call the phenomenon pattern maker's contraction to avoid confusion in terms. Interestingly, ice expands to a larger crystal structure than the atoms of liquid water, and that's why ice cubes push up out of the ice cube tray and are larger. Well, the opposite phenomenon occurs with metals in casting molds. The metal wants to get smaller and the mold pushes back. As the crystal structure is formed, the dimensions get smaller, pulling away from mold walls and often causing distortion as the mold pushes back in local areas. So the consequences of shortening dimension lengths is difficult to predict, but it gets worse. This is research done in our American Metal Casting Consortium, funded by the Defense Logistics Agency and conducted by Penn State. And what we see here is the contraction rate based on feature length on the x-axis, and just look at the variation from contraction, which we expect, to some expansion, which we wouldn't expect, but the overall nominal rate is 2.1% for carbon and low alloy steels, which is what these experiments were conducted for. But in this case, we actually got 1.6%. So you can see that even as a longer dimension where the one standard deviation gets smaller, we still have significant variation. The consequence of this wide variation in pattern maker's contraction rate is difficulty in centering dimensions within their specified tolerance range. Here we have a 10-inch dimension, and the tooling was built for this casting, and we used an expected 2.1 pattern maker's contraction rate, but only got that 1.6% rate that I highlighted on the prior slide. So our process is capable of meeting the dimensional tolerance band specified, but our center of the dimension is off by the amount of the error in pattern maker's contraction estimate. So consequently, some of the castings are outside of specification, not because the process wasn't capable, but because the dimension wasn't centered because we missed our pattern maker's contraction guess. So pattern maker's contraction rate is a guess made by the mold cavity tooling builder, and the data shows why that guess is problematic, and it shows why dimensions are so difficult to achieve correctly in the first article inspection. But that data with all the variation was just for one metal alloy family, the carbon and low alloy steels. Look here at all of the many metal casting alloys, and look at the difference in the center column, which is the standard parameter, inches per foot of contraction, and just look how much the median rate for each of these alloys differs. When I was making casting, here's a chart that I used to help me and my mold cavity tooling builder collaboratively make better pattern maker's contraction rate guesses. Listed in the rows are all the features of the casting design that I was worried about. They were either critical or significant features with tight dimensional tolerances, or they would be formed in the mold in a way that I thought could cause contraction rate problems. I would take my chart to the mold cavity tooling builder, and we would collaboratively decide what rate to apply on each feature that was listed. If we missed, we missed. We would have to fix the tooling and make new prototype castings to see if we did fix it, but we tried, and at least we thought about it carefully. Now, look at this center column labeled full, marked in light orange. Full means that after we chose the contraction rate, we built the tooling on the large side of the dimensional range. For risky dimensions, that meant that when we missed the contraction rate, which we sometimes would, all we had to do was remove some tooling material to fix it. With metal tooling especially, having to add small amounts of material to the tool is a disaster for tool life. The next most significant variable in the control of dimensional tolerances, but much more controllable, is mold degrees of freedom. In other words, freedom of movement in the assembly of the mold cavity. Most casting molds are assemblies of mold halves, cores, chills, and perhaps printed mold elements from additive manufacturing, but not all molds. Some are close to monolithic, most notably investment castings and sometimes die castings and lost foam castings. As we will see in an upcoming slide, even those mold cavity making processes can have degrees of freedom that affect dimensions, but not as much freedom relatively speaking. Well, here we see a typical situation in a horizontally parted sand mold. Encircled is a tall core that is set in the bottom half of the mold. It has 2 degrees of freedom in the green horizontal box. It has a core to mold degree of freedom as that core sits in the bottom half of the mold, and it has a degree of freedom across the mold parting line as it goes across that parting line and connects with the top half of the mold. The consequence of the variation in the mold assembly results in a tolerance coarsening of 150% or 1.5 times the base tolerance of the features formed in the bottom half of the mold only. So if the tolerance for the hole formed in the bottom of the tall core is plus or minus 2 millimeters, then the tolerance for the hole formed at the top of the core is 1.5 times that best tolerance, or it becomes plus or minus 3 millimeters. Here are two of the most accurate mold cavity making process. First, the investment casting process here, and we see the wax pattern, but it has a ceramic core here, another ceramic core of which there are another piece that sits in here. Part of the ceramic core assembly in the green wax is shown there, and there are degrees of freedom in the assembly of those ceramic cores and match lines where those ceramic cores join together. In the lost foam process, to make this styrofoam block, assembly of styrofoam patterns vertically create the entire geometry of the block, and there is registration issues and gap issues in the assembly of the styrofoam layers. So even the most accurate processes do have degrees of freedom, just on a more limited basis.
The idea of draft is most easily visualized as a cupcake in a cupcake baking pan. If the pan doesn't have slanted sides in the cupcake pockets, the cupcake can't be removed from the pan. Since baked cupcakes don't have much tensile strength, very much pull on the cake will break the cupcake. So that slant in the pan pockets is largely due to enable release from the pan with little force to get the cake to release from the pocket's side surfaces. Well, pulling mold cavity elements out of a tooling to form casting molds is the same. Some materials like wax are slick and relatively strong, so the slant can be small. Other materials like green sand are not very strong against a pull, so the slant has to be much larger. And getting a solidified casting out of a metal mold requires a much larger slant. So that slant is commonly expressed as an angle known as draft. For the metal casting processes and its tooling types, that angle commonly varies from ½ degree to 3 degrees. In some cases, it can be as large as 5 degrees. Standard practice in specifying draft and casting designs is to define it as the draft angle. But that angle, which seems appropriate enough, causes first article approval problems all by itself. Let me explain why. Here we see an as-cast surface on the left end of a casting that has two molded parting plane options. One option has the casting split through the center, and the draft angle creates an offset that is the same on each side of the casting end feature. The second option has the pattern plane following the bottom surface of the casting. The same draft angle now creates an offset that is twice as large as the offset created by parting plane option 1. As a consequence, the large offset may cause problems with the dimensional tolerance profile of the casting's left end tolerance. Next, we see another draft option that can cause a first article nonconformance issue. Parting plane option 2 creates two different draft draw lengths. In order to make the left end feature have the same size at the top and the bottom, the draft angle maximum is violated. That angle maximum violation may be called out as a dimensional nonconformance in the first article test. Here is a real DLA casting that suffered a first article test conformance involving draft. It is an aluminum structural casting for the T-38 airframe. In the next slide, the allowable 2-degree draft is shown in dark pink, resulting in the bottom of the end feature being out of tolerance on the left side. On the front of the casting, the same amount of draft offset causes a low dogleg feature to be out of tolerance on the short side. The summary of draft angle versus draft offset and draft draw length concludes our discussion of the reasons for dimensional nonconformances in first article inspections. You will recall that the major cause of first article nonconformances in DLA's study of all causes was surface finish. Together with dimensional issues, surface finish inconsistencies is other major contributions to the 89% of all casting related first article nonconformances. Here's Mike again to explain the surface finish.
We've now seen the factors that complicate dimensional tolerance compliance in first article inspection, but now let's look at the other major cause of casting nonconformances, which is surface finish. Surface finish, along with dimensional tolerances, compose 37% of all casting nonconformances in that DLA Pareto chart, and 89% of the nonconformances that are specific to the casting processes and the casting tooling. So first of all, let's just look at how surface finish should be measured. This is the National Aerospace Standard 823, also known as the GAR Cast Surface Comparator. And basically, these surfaces are replicated of actual casting surfaces. And this is the best way to evaluate a casting surface because you can hold the plate up against the light at different angles. You can touch it, you can touch the casting, and you can make a visual and tactile comparison of surface finish most effectively this way. Well, what then complicates the surface finish if that's all there is to it? Well, here is the reason. Here is a mold filling. This is an aluminum automotive casting in a safety critical application. And it is being filled as it really occurs in the mold. So what we're seeing now is the mold cavity being filled, and you're seeing attachments to the mold cavity that enable the filling of the mold and also to feed solidification shrinkage to achieve the mechanical properties that are specified. So all of these attachments that we see from the mold filling system, from the risers which feed solidification shrinkage, and even some surfaces like this may have a chill against it to help it solidify quicker. All of those surfaces aren't like the surface comparator that we just looked at. These surfaces are actually cut away by a cutting operation of one kind of another depending on the alloy. Then it is lightly ground to try to replicate this circular profile, and then media blasted to try to make the grinding marks go away and look like the as-cast surface as much as possible. Well, what do these surfaces actually look like? This is on a steel casting, and this is that same kind of process interface geometry that we saw in the video, attached to the casting, delivering the liquid steel into the mold cavity and helping it set up with solidification gradients that meet the mechanical properties in the microstructure. And these are what these cut-off surfaces actually look like. You can see they're a little higher than the adjoining mold walls. There's a little bit of surface roughness because it's hand ground and then media blasted to look as close to the as-cast surface as possible. And incidentally, here is the parting plane of the mold, top half and bottom half, that you can see clearly is somewhat different than the adjoining smooth surfaces on each side of that parting plane. Well, notes like this help. Gates, risers, flash, and parting lines shall be trimmed flush to 0.03 of an inch max above the adjacent surface unless otherwise specified. And that's the kind of call out that allows this raised surface here and here.
As we have seen, all castings have surface anomalies from process interface geometry. That is, the gate, riser, chill, and vent attachments that have been cut off. The remaining stubs are ground down by hand to match the adjacent as-cast mold cavity surface finish as closely as possible, and then the casting is media blasted to smooth out the grinding marks. The same surface treatment process is applied to another cause of casting surface anomalies. This cause is in-process weld rework, a normal finishing process on any weldable metal casting alloy. In-process weld rework is a normal consequence of liquid metal mold filling, solidification surface imperfections, or finishing handling. Most common anomalies from pouring and solidifying are non-metallic inclusions and incomplete edges on fine corners of the casting geometry, as we see here. Casting finishing processes cause surface anomalies too. Most common in finishing processes are the dents and dings from handling, overgrinds, and small quench cracks from heat treating. Extremely shallow surface anomalies are often blended away by hand grinding, leaving a very shallow minus metal profile on the casting surface. Generally, however, the anomaly is excavated away by deeper grinding or arc air. The cavity is cleaned by light grinding, and then a matched alloy weld wire or weld rod is used to build the cavity back up to and beyond the adjoining as-cast surface. And that's what we see here, the weld buildup of a matched alloy over the excavated and cleaned cavity. After heat treatment, the plus metal of the weld is hand ground flush with the adjoining as-cast surface, and then the entire casting is media blasted to help match the weld rework area to the rest of the as-cast surfaces. And that's what we see in the image inset below the unfinished weld. For most commercial castings and many military castings, there is no specification prohibiting or limiting in-process weld rework. And AMS 2175 is silent regarding whether or not in-process weld rework was applied to casting surfaces. 2175 simply defines the quality of the casting's solidified microstructure via non-destructive testing. Next, let's look at why that silence exists, as well as preferred ways to allow in-process weld rework in critical service casting applications.
Here we see E357 T6 sand casting coupons, unwelded, welded halfway through the thickness, and welded completely through their thickness. No weld is red, half weld is blue, and full weld is green. For 1,000,000 cycles, the cyclic tensile stress to failure, the full weld was the same as the red no weld coupons, and the half weld coupons sustained about 20% higher cyclic tensile stress to failure. Here's a well-crafted drawing note specifically allowing in-process weld rework and differentiating grade B and grade C solidification areas in accordance with AMS 2175. Returning to the same example of the in-process weld rework of the aluminum casting with the sand inclusion defect, here is the non-destructive testing documentation that the weld repair we see meets AMS 2175 grade B solidification integrity. Now please meet our casted teammate, Keith Sturgill. Keith is based at the Defense Logistics Agency's Aviation Supply Center in Richmond, Virginia. Keith supports casted efforts from inside DLA as a graduate materials engineer and a career in the Navy specializing in jet engine materials and components. Keith will give us an overview of the roles of the 4 players involved in the preparation and inspection of DLA legacy casting first articles. Here's Keith.
As Mike has said, there are 4 who's in the production, inspection, and approval of DLA cold start legacy casting procurements. As an overview and as a notional estimate using the 80-20 rule, here are the relative responsibility percents for casting quality of the 4 who's that Mike talked about. First, the cold start new awardee has about 80% of the responsibility. Second, the first article inspection lab has about 10%. Third, the engineering support activity about 7%. And then lastly, the Defense Contract Management Agency has about 3%. In addition to having the most responsibility by far, the cold start new awardee is typically a team of suppliers, frankly, in both the private and military/aerospace sectors. The recipient of a purchase order or a contract typically doesn't think of their business as a member of a team of businesses. 70 years ago, when manufacturing businesses were vertically integrated, one company had the breadth and depth of talent, resources, and plant equipment to manufacture complex engineered components, complete and in-house. Occasionally, a metal caster will encompass all necessary processes but it is now rare. Today, the integrated result is normally accomplished cooperatively by separate manufacturing businesses. Most commonly, those separate businesses are the metal caster, a mold cavity tooling builder, a machine shop who may also fabricate a casting into a larger component or fabricate a net-shaped feature onto a casting. Then there's a heat treater and a coater. At maximum, that's a team of about 5 separate, distinctly different manufacturing businesses. But most often, these 3, 4, or 5 partners in their separate businesses don't collaborate much in the midst of their complex manufacturing task. To be done well, these 4 elements of manufacturing engineering must be integrated. First, the mold cavity making process choice. Second, the mold cavity tooling design and construction. Third, fixtures for processing as-cast surfaces that will assure consistent fit-up in machining fixtures and/or final assembly. And fourth, the machining fixtures themselves. Instead of integrating their engineering efforts for a more uniform result, it is typical for these separate businesses to make their manufacturing process and tooling design choices independently, and then try to pick up the pieces of dimensional problems, mostly as the partners work to prepare the first article submission. In this disjointed scenario, it is difficult to get every detail of so many dimensions and surfaces completely correct. Before I return to describe the roles of the first article testing lab, engineering support activity, and the Defense Contract Management Agency, Mike will explain how the Cold Start new awardee metal casting supplier team could better integrate their efforts to achieve a first attempt first article inspection approval.
Here's a Gantt chart that I've used for another purpose, but I modified it to illustrate the manufacturing engineering tasks that are needed to first launch a new casting design. So on the vertical axis, years ago, are the tasks, both metallurgical engineering and manufacturing engineering, to get to the point where you have prototypes and you can do strain life testing and then ultimately build production tooling, go through the same kinds of manufacturing engineering and metallurgical engineering steps to get to first article approval and then begin casting production. Well, now, years later, we have a second Cold Start new awardee, or third or fourth, who has to repeat most of these same metallurgical and manufacturing engineering steps. In fact, the only ones that really aren't repeated are the ones that have to do with the strain life testing and durability testing. But otherwise, all of the first article steps in prototypes, getting ready for a first article, getting a first article approved, and then getting the production underway, the DCMA approval to produce, as we have learned in the aircraft sector at DLA, can be as much as 800 days. In fact, that's the average of airframe castings that are in this legacy category, manufactured primarily now by machine shops in partnerships with the 4 other businesses that we've talked about. So this whole process has to be started afresh, has to be done immaculately, and is most likely being done by a machine shop. So what can we recommend to make success more likely than lost time, lost resources, and 800 days? Here's the skeleton of a Venn diagram defining the roles of the 5 separate cooperating businesses that are the metal casting supplier team. We will assume that the Cold Start new contract awardee is the machine shop. Might also be the metal caster, as it traditionally has been, but now most likely is the machine shop. In the middle is the mold cavity tooling builder, who will collaborate with both the machine shop and the metal caster, whether it be intentional or not, whether it be integrated or not, but it should be both. Well, where are the other two? The heat treater and the coater are around the perimeter because they might be part of the metal caster's vertical integration. In other words, many metal casters have their own heat treat facility. Sometimes they have their own coating capability. In that case, there are only three in the center cooperating business partners. Well, here are the roles that all of the big three play. The machine shop makes the machine tool choices and makes the fixture designs to get from as cast to a final net shape. The metal caster makes the mold process choice, deals with the dimensional variables in the design and construction of the tooling and the choice of the mold process integrated together, does mold filling and solidification simulations. The mold cavity tooling builder is involved in the functional gauges and straightening fixtures that usually are part of the metal caster's finishing process. Also does the CNC toolpath software to actually create the mold cavity tooling. And also has the mold cavity tooling builder the additive manufacturing technologies either in-house or among partners that have additive manufacturing technologies. But there's another significant capability that the mold cavity tooling builder has that's unique. It's the mold cavity tooling builder that builds the solid models that we talked about before. First, the solid model from the 2D drawing, if it's a legacy casting with a TDP package that is old and doesn't have a solid model, which is typical, and has all the software expertise to make the solid models not only of the 2D drawing conversion, but also to add draft, the mold parting planes, the match planes between cores and slides and assemblies of the mold cavity, and the draft. Also has expertise in geometric dimensioning and tolerancing, and has access to know-how that has application in how all that technology is applied to the three versions of the solid model. Well, Gary Burrow, who spoke to you about draft, is one of these mold cavity tooling builders. And the green areas are so significant, it's our recommendation that regardless of who holds the contract for the cold start new award, whether it be the machine shop most likely, or the metal caster, it's the mold cavity tooling builder that should be the technical lead of the intentional collaboration to make the manufacturing engineering happen successfully. Well, Gary is one of those guys, and here's Gary to explain how he does this.
Over the 4 generations of the Burrow family in the mold cavity tooling design and construction business, we've cultivated individual relationships with a variety of metal casters serving the Southern California commercial, defense, and aerospace industries. Given that variety of casting and uses, we developed a wide spectrum of expertise in mold cavity making processes and alloy families. Now I have a national presence as a technical lead in the metal casting supplier teams that I serve. Having established that expertise as technical lead, I frequently take turnkey responsibility as the contract or purchase order holder for delivery of finished castings, including DLA cold start legacy systems. As Mike was describing the roles and abilities of the 5 primary business partners of a metal casting supplier team, those areas he highlighted in green are what I do. In my turnkey role, being responsible for delivery of finished castings, here's a list of what I do in collaboration with my metal caster, machine shop, heat treater, and coder partners. Initially, during the bidding process, I make sure selection based on the requirements of the finished casting, including the best mold cavity making processes based on the dimensional, surface, finish, and solidification integrity required in the finished casting specifications. What additive manufacturing technologies could augment the mold cavity making processes, either in direct printing of tooling elements or direct printing of mold cavity elements in natural sands, ceramic sands, or ceramics. Even metal mold elements, or chills. The type of machine tools and fixturing approaches required to convert some as-cast surfaces to finished machine surfaces and fabricating the casting into other finished geometries like threaded inserts, bolt-on, or welded-on other geometries. The best metal caster nationally that is capable of producing the best casting using that mold cavity making process. Selecting a hot isostatic press or hipping press provider if the solidification integrity and dynamic property requirements are very high beyond the capability of the chosen mold cavity making process. The best heat treater based on the chemistry and microstructure of the chosen alloy and the probability of fixturing for heat treat and or fixturing for straightening afterwards. The coater based on the chemistry and processes of any specified coating, including markings. Whether I wind up being turnkey source or the technical lead as a collaborating partner in a metal casting supply team, here's what I do in those green areas of the manufacturing engineering collaboration graphic. If no solid model exists, we build a solid model of the as cast and or finished casting from the 2D drawing. Based on the manufacturing engineering collaboration with the metal caster and the machine shop, we build a modified solid model that adds the mold parting planes, mold draft, core to mold match lines, core print to mold match lines, core and core print drafts, chill prints and chilled print draft, and connection surfaces for the in-gates, risers, and vents. This geometry is what defines the actual as-cast features of the casting as it is formed by the liquid metal. As a preface to estimating the pattern maker's extraction rate for all of the manufacturing in the second model, I convert all of the GD&T tolerances of position and profile to old school plus minus coordinate tolerances. I do that because building tooling for the molding cavity has to be converted in plus minus just as the dimensional capability of the mold making processes is necessarily expressed in the old school plus minus process. To accommodate pattern maker's contraction of the second solid model's features are increased in size based on the alloy's pattern maker's contraction rate. The metal caster and I collaborate on what that normal rate should be, which varies substantially by alloy. It should be modified for each significant or critical dimension on the casting. Pattern maker's contraction rate is always a guess. Mold cavity builders always make the guess, but it is best to collaborate on guessing with the metal caster's experience included. Better guesses make fewer tooling adjustments to correct dimensional and non-conformancies later. And along with the increased model size for pattern maker's contraction, if the net shape is to be upgraded by machining, we add machine stock to the cast surfaces that will require a machine. From the modified solid model, we use any of the following manufacturing technologies to create the tooling, tool elements, and direct printed mold cavity elements. Subtractive tool path geometry and CNC machine tools to form mold elements, core box cavities, and chill mold cavities. Subtractive or additive technologies to create cavities that become core boxes or molded pattern elements. Additive technologies to make quick prototype in sand molds or investment mold patterns. Additive technologies to make production printed investment patterns or printed sand or ceramic mold cavities for sand molds. We mold cavity tooling builders either have to have or have access to the additive manufacturing technologies needed. Some of the technologies are located at universities, AM providers, or AM service bureaus. Even direct printed sand and mold elements are durable enough to be shipped to the metal caster's facility from AM sources around the country. For the different fixtures that are needed for processing from the as-cast surfaces, we can produce a 3D solid model that removes the casting manufacturing features such as core and chill prints, leaving only the drafted surfaces with mold, parting, and core match lines, in-gates, risers, vents, etc. We can then remove the pattern maker's contraction size increases. For building fixtures for processing as-cast surfaces, including heat treat and machining setup fixtures, this third solid model is a great asset. Since I am responsible for the pattern maker's contraction estimates, which are at best educated guesses, I encourage the metal caster to make quick, unfinished prototype castings to see how significant and critical dimensions actually come out to be. I can help with versions of this production tooling made quickly for the prototyping from additive or subtractive manufacturing technology that I either have or have access to. Not many of my mold cavity building peers take the initiative like I do to be the technical lead in integrated manufacturing engineering for first article approval success. But they do have the know-how and assets to collaborate. They just need to be asked and encouraged to make the technical leadership for everyone's benefit. Julia will now rejoin us to conclude part one and provide a quick summary of part two.
From a Defense Logistics Agency study of legacy casting first article nonconformances, we learned that 74% of nonconformances are attributed to dimensions and surface finish. This is known to be typical across defense and commercial first article inspections of castings. Specific to cold start or new awardee legacy casting launches, amazingly, the average lead time for successful delivery of a production order for airframe castings is 800 days. The majority of that time is lost in repeated efforts to accomplish first article approval. We examined the reasons why, and we explored collaborative manufacturing engineering methods among all the businesses in a metal casting supplier team to mitigate the reasons for inspection nonconformances. Soon, part two of this two-part webinar series will be available to you. Since machine shops are now 70% of the new awardees for DLA legacy casting procurements, part two explores the attributes of bringing as-cast surfaces to net shape upgraded surfaces. Also explored are the manufacturing engineering methods used by machine shops who specialize in machining castings. Finally, Keith Sturgill will be back to share his insights regarding how the first article inspection lab, engineering support activity, and the Defense Contract Management Agency can play their roles to the benefit of earlier first article inspection approvals. So please, join us again for part two in this series. In the interim and beyond, part one will be available to watch on the AMC website at your convenience.
All right, so good morning, everyone. My name is Julia Speaker, and I'm going to ask all of the panelists to start sharing their webcam so we can start on with our Q&A. So I am the Cast It team lead. Before we begin, I'd just like to take a minute to introduce Cast It, a little bit of what we do and who we are. So we are a team of application engineers, and we work to solve both technical and procurement issues regarding castings. So if you look at in the handout section of your GoToWebinar control panel, you'll see two handouts that are available for you to download. The first is a Cast It one-pager, and it details just some of the types of projects the team has worked on. It also links to several resources on really a pretty wide range of casting topics that we have put together and developed. The second handout is the Casting and Forging Assistance handout, and it just covers ways that we may be able to help you, as well as different ways on how to engage our team. So without further ado, let me introduce the Cast It industry experts, and then we'll get started on our Q&A. So in no particular order, since all the webcams may look different on your screen versus mine, we have Gary Burrow, who is a fifth-generation pattern maker and all-around casting guru. Dave Powlite, who is the VP of Technology at Steel Founders Society of America. Mike Gwynn, who is a casting design expert. Dick Tiano, who is an expert in all things 3D data. Keith Sturgill, who's a metallurgical engineer and an expert in all things DLA and government processes. And then last but not least, we have Jenny Swaggart, who is the American Metal Casting Consortium Program Manager. So combined, the Cast It team has over 150 years of experience in the metal casting industry. So these are a great group of guys to ask any sort of questions you have. So we'll go ahead and open it up. So some of you guys may have been putting in questions as we go. Feel free, as we keep this discussion moving, to add even more questions to the list. All right. So this is probably a question for Mike or Gary. It seems like there's a lot of educated guessing, based on a lot of good prior expertise when you're dealing with making castings. Is there any sort of like simulation software or algorithm that can help with this? And do most suppliers have that kind of capability?
I'll take first shot at that, Gary. Simulation of pattern maker's contraction is just a bridge too far. And the reason that it is so difficult, and it's been attempted, and there are programs underway to try to do it, but you have the metallurgical differences that you saw in that table of all of the pattern maker's contraction differences from one metal casting alloy family to another. But you also have the constraints in the mold. You know, metal molds, sand molds, ceramic molds all have pushback at different rates. So when you look at the combination of the contraction of the metal and the pushback from mold elements, it's such a complicated problem that it's unlikely that simulation will be able to predict pattern maker's contraction more accurately. I'll let Gary comment on that further, but we have wonderful simulation tools in the metal casting industry, and they've made huge differences in our ability to meet mechanical properties at a very high level, especially in the light metals where reducing mass is so important. But dimensional capability and the biggest single problem being pattern maker's contraction, that one is going to be a long, long way off into the future before it can become a simulation tool.
Gary, I think you're muted still.
Hear me now?
Yep, we can hear you now.
Mike is correct in what he's saying there. The simulation becomes very difficult because you're dealing with so many different medias, and basically it's the restrictions of the mold that don't allow it to shrink that causes the biggest problem. When you restrict that shrink, well, then the casting wants to hot tear and pull itself apart as it cools. So then if it can't shrink properly, you have to ensure you put risers and gating on it to be able to feed the metal to keep it from cracking like that. So again, it's an educated guess, and the experience of knowing by looking at a model where those restricted areas are is where we may put our variable shrinks on and different things. And the cross section of the metal can also affect that too. A heavy section may burn in as well as contract in the cooling process. If it's a thin section being restricted, like a core up through the middle of a part, then you run into those hot tearing problems. So then you have to look at how do I resolve those issues. Even if I adjust for the shrink factor to make the dimension come out correct, I still may create a problem in hot tearing the part. So there's multiple factors that come into that requirement.
All right. Thanks, Gary and Mike.
Julia, I had a question. I saw that there's a couple of suppliers on the line, and when I think about looking at it from the standpoint of a foundry or a machine shop looking to bid on a part for the government, if I see something such as a limitation for in-process welding or maybe a surface finish that I'm uncertain I can achieve with my process, and this is questions probably for Keith, what's the right code of conduct if I want to have a discussion about what's possible or getting a waiver or deviation in place?
I think that's a really good question, Dave. And I think there's a lot of folks on the call that recognize that we're buying parts at DLA for weapon systems which are long gone out of production, most of them, and we're buying parts for foreign military service sales. So we're buying stuff that's long gone out of production, and so as we talked about during the webinar, most of these parts are what we call new cold starts. So whoever is going to make them, they're going to have to start from zero and go through developing the whole process. So as you said, in reviewing the tech data package, maybe they're noticing that there's nothing in there that allows in-process weld repair, or maybe there's something there that there's a note that says if you're going to do it, you have to do a weld map and request that and get approval in advance. That's typically what manufacturers see, that okay, if you want to do any welding, you're going to have to do a weld map, show where you're going to do it and what the volume of the weld metal is that you're going to be putting into it, and get that specifically approved ahead of time. Well, that's kind of problematic for manufacturers, and this case-by-case basis is
is very difficult. But what Mike talked about, we found that the AMS spec is really silent about this. And if you look into the specs, in-process weld repair, there's nothing wrong with it. So to answer your specific question, what I would do if I were a manufacturing outfit that I was looking into, hey, I want to be able to, I'm getting some small defects occasionally on the surface, handling damage or whatever, and I'd like to weld repair these. I would submit the request for variance and ask for, specifically say what you want to do and why you want to do it, and then reference the fact that the AMS spec is silent about it. Really, is it's okay to do it. So I would go the RFV request for variance route.
Thanks, Keith.
Thanks, Keith. All right, Gary, I'm wondering if you could just talk a little bit more about your experience in using this integrated kind of metal casting supplier team approach in providing castings, and maybe if you've ever had an experience or any of your fellow colleagues have had experiences in supplying a part that had a less integrated approach. Could you talk about the difficulties that you faced in doing that?
Well, we definitely don't get it right every time. So, yeah, as stated in there, I try to put a team together that I trust, that I've worked with in the past, that I have good confidence in. Sometimes that's not available. We have to go out, reach out to a new supplier that maybe we haven't dealt with before. So then you kind of build a rapport with them and get a comfortability feeling that you can work together and do this, which is actually pretty easy. Everybody wants to do business, not all with the government, but so pretty much, you know, we have a kind of a plan of attack of how we're going to do each of these parts, look at it from the standpoint of the castability of it, what the surface finish requirements are, all those features, and then take it on to the next level of how is a machine shop going to be able to set it up. And the thoughts that I have of a machine shop, maybe somebody, they think a horizontal machine is better. I may think a vertical machine is better. And those things, which would cause different fixturing. And the biggest thing is that you have to ensure that the setup points that you're going to inspect the casting to and straightening are the exact same points that you use when you machine the casting. Because I can grab at a different place and get a whole different set of readings for dimensional processing. So we have to ensure that the same points are used all the way through the process. So from that, and then once you get onto the coatings on that, then it's kind of requirements are pretty set. You know, the drawings typically say, you know, passivate, go on to some kind of a phosphate coating, something like that, which surfaces the mask. Holes are typically have some kind of masking, especially if you're going to get threads in them or something like that, or have an insert put in them. So all those steps that you have to look at through the whole process. So we kind of do a kind of a loose process control of how we would handle each of those items and who's going to take care of each one. But generally, if I'm the lead, I'm controlling all of those things and ask for their input in order to create that flow path that's going to happen. Does that answer your question?
It does, Gary. Thank you.
Julia, may I chime in on that with regard to how you handle as separate businesses, you know, what your margins are? So like Gary, when I was producing castings, I was typically the lead and I had 4 partners. I did my own heat treating. So I had a coder, had a machine shop and my own team. And I never discussed, we were all collectively aiming at the lowest cost final assembled net shape. But I never asked my machine shops, my coder, my mold cavity tooling builder about their margins or what their pricing to me might be, if I could lean on them to change pricing and make it easier for me, since I was responsible for the finished part, to meet my customers' target pricing. We just went after cost. We went after collaborative efforts of manufacturing engineering to get cost out, and never once did I ever discuss margins with any of my partners.
And nor do I.
Great input, Mike. All right. So I don't see any more questions from attendees. So we still have a few minutes. Mike, I wonder if maybe you could give us say a little bit more than I did about what we can expect in part 2. Give us a little teaser.
Well, I think what Gary spoke to towards the end of this part 1 is the part that will be expanded the most, and that is the fact that the solid models in 3 different versions are Gary's responsibility as the mold cavity tooling builder, and how critical it is to build those solid models, because in today's technology you really can't go forward without solid models. And in the typical DLA cold start, there are no solid models to start with. You just have a 2D drawing and a technical data package to flesh out all the other requirements. So we'll talk a lot about with really specific examples, show pictures of solid models, some of the different versions of solid models, some of the things that you run into as you plan the manufacturing engineering of the processes from those solid models, with lots of pictures. So that would probably be the one thing that you'll see in part 2 that explains what Gary really does.
And just as an add on to that is that in our breakdown of what we're going to do, the number one first item is create the CAD model, because in today's world, everything is going to work off of that model. So part of that problem is working off of these legacy 2D drawings is a lot of times it was a French curve that blended a surface, or, you know, a pattern maker to blend notes, things like that. So now when you get into modeling, many of those things become much more difficult. So you have to either try to figure out, or sometimes even go back and ask for a clarification off of the drawing as to how you could be able to create that model. The first stumbling block you may find is in trying to make a model that meets the requirement of the drawing, because things just don't match that you couldn't even tell back in the days of hand drawn. And typically the engineers that come over to the pattern shop and they say, well, just blend that in, ferret, you know, move a wall a little bit, whatever, make it work. Well, that information never got back from a red line drawing onto the final revision drawing. So it just has been laying there as a problem ever since, and everybody worked around it. But in today's quality world, that doesn't fly. You just almost impossible to get it through if it gets all the way to a finished part, and then how do you resolve it? So you try to resolve the issue up there when you're creating the model. Send the request for variance or clarification off to the DLA at that time, rather than just keep getting further in the hole and have a problem when you got a lot of money invested in it. You want to resolve those issues up front. And typically today it gets back to the engineers, ESAs, and they don't know how to answer the question either. So then you got to kind of collaborate back and forth, like we would have done in the old days with an engineer come over and try to work up a design that is acceptable to everybody. And then that has to get documented at the ESA's facility to ensure when we come through with whether it's a revision change or just a clarification note, that when this part comes through for final inspection, that everybody knows what was talked about and it is able to be approved. You know, we've had a lot of issues that all the way think we're going the right path, and then we can't get an approval at the end.
Yeah. So Julie, the second part of your question, and I'll let Keith speak to this specifically. The other really big part of part 2 webinar is Keith's discussion of what Gary just said, because 80%, as Keith said in today's webinar, of the obligation to get a first article approval success lies on the cold start new awardee. But there's an engineering support activity, there's an inspection lab at the site that's responsible for the part, and there's the Defense Contract Management Agency that have roles in this. And Keith expands how those other 3 players in the inspection and approval process can help. And Keith might want to give us a little preview of that.
Okay, thanks, Mike. Yeah, you're right. 80% of the responsibilities, of course, it falls on the awardee. They've got to figure out how to make the part. But the government has some latitude to help so that we can work together and team and get that 800 days down to something more helpful to the DLA customers. So we're going to talk on part 2 a little bit about some of the latitude that is built into the FAR, where the ESAs have some latitude, particularly conditional approval. And so the government has some ways that they can help. I think we need to look at the process as a partnership. We're not working against each other here. We're working together. So the government has some latitude to help. And the other thing is, together, the reality is the 80% responsibility, part of that the manufacturer has, part of that is, unfortunately, he's sort of vetting the TDP. So we need to work together to find those issues in the TDP, such as out-of-date specs, or maybe the latest drawing revision's not there. Some of those type things that we can together fix. So next time, I think it's going to be pretty interesting, as you're going to see the government has ways that they can help out.
And then lastly, the big part that Julia mentioned in her comments as she wrapped up was the fact that we're going to talk about what the machine shop's obligations are and their capabilities. And Dick, who hasn't said a word yet, is going to get a chance to be a big part of what can the machine shops do to drive the bus to successful first article approvals, because 70% of these cold start new awardees for DLA are now the machine shops. They're not like the Mikes and the Garys. They are like Dick. So you might comment on that, Dick, if you want to.
So Dick, it sounds like you're still muted.
Yeah, I just unmuted. So we'll talk a little bit about the different machine shops. Some are just casting houses that only machine and work on castings, and other machine shops do machining from wrought iron, and we'll discuss the differences in machining from a wrought iron block or a bar versus machining a casting to reduce or actually to have the least amount of chips from a good machining operation. So we'll touch on that in detail in part 2.
All right, that was a great summary, guys, of what part 2 is going to entail. So it looks like we're just a couple minutes past 12. So I want to thank all of our attendees, as well as our industry experts, for participating in today's First Article Success webinar. So part 2 will be held on March 23rd at 11 a.m. Eastern. A registration link is going to be sent out later today. In addition, we really do value your feedback, so a very brief survey will pop up immediately following today's webinar. We would really appreciate it if you take a moment and fill this out. If you have any questions about any of the content that was covered today, or the resources provided, or really anything regarding castings, feel free to reach out to me, and I'd love to help out and discuss further. All right, well, with that, I hope everyone has a great day.
Thank you.
Thank you.
Bye, everyone.